What happens when you compound interest not once a year, not monthly, but every single instant? You might expect the answer to grow without limit. It does not. No matter how frequently you compound, the result approaches a ceiling. Watch as n grows from 1 to 1 million. The result converges. Each new decimal place costs 10 times more iterations than the last. The number slows, settles, and stops. That limit is 2.71828 and we call it E. And its logarithm is the natural logarithm. Humans chose 10 as their base for counting because we have 10 fingers. Convenient. Arbitrary. Entirely our decision. Computers chose 2 because a transistor has 2 states, on and off. Again, a choice made by the constraints of the machine. But long before humans were counting, long before any machine existed, nature had already settled on a different base. Nobody chose E, no committee agreed on 2.71828. It emerged, unbidden, from a single question: what happens when something grows at a rate proportional to its own size? The answer, always, is D. Let's look at another example. We have one bacterium placed in a warm Petri dish with plenty of nutrients. E. coli divides roughly every 20 minutes. One cell becomes 2. 2 become 4. Just a cell doing what cells do, growing at a rate proportional to its own size. Now the divisions accelerate. 64. 500. The dish begins to fill. 4,000. 32,000. 262,000. 2 million. 16 million. 134 million. 10 hours, 600 minutes. And we have over 1 billion cells. We wrote it as 2 to the 30, counting discrete doublings. But E. coli does not actually jump in steps. Every ribosome, every molecule, is replicating continuously, every instant. The correct model is n equals e to the r times t, where r is the continuous growth rate ln to divided by the doubling time of 20 minutes. That gives r approximately 0.0347 per minute. Plug in t equals 600 and you get e to the 20.8, which is exactly 1 billion. Now invert it. If n equals e to the rt, then ln of n equals r times t, and t equals ln of n divided by r. That formula, t equals ln n over r, is the natural logarithm doing its fundamental job. Given a population produced by continuous proportional growth, it tells us how much time has passed. The bacteria did not choose E. The mathematics of proportional growth had no other option. Let us draw both curves on the same axis. First, the dashed line y equals x, which will act as our mirror. Here is e to the power of x in gold. It rises steeply. This is the exponential. It tells you how large the population is after time x. And here is ln of x in t. Notice it is the exact mirror image of e to the x, reflected across the line y equals x. They are the same relationship, read in opposite directions. Take the point x equals to on the exponential curve. E squared is approximately 7.4, that is the population at time 2. Now mirror that point across the line y equals x. You land on the logarithm curve at x approximately 7.4. The natural log of 7.4 is approximately 2. The exponential asked, after 2 units of time, what is the population? The logarithm asks, given a population of 7.4, how much time has passed? Same relationship. Opposite direction. Here is an epidemic curve plotted on a normal linear scale. For the first 10 days the case count barely registers. It looks almost flat against the axis. Then it bends upward. Then it explodes. On day 5, 15 cases. A handful. The natural log of 15 is approximately 2.7. Calm. Under control. Nothing to worry about. Day 10, 244 cases. The case count has multiplied by 16 since day 5. But the natural log has only moved from 2.7 to 5.5. An increase of less than 3. That still sounds manageable. Day 20, 60,000 cases. The count has multiplied by 246 since day 10. The natural log has moved from 5.5 to 11. Again, an increase of about 5.5. The same fixed step in ln, but an explosion in reality. Look at the pattern. Each 10-day window, the case count is multiplied by roughly the same factor, 244. But the natural log increases by the same fixed amount each time, about 5.5. That is exactly what exponential growth means. A constant ratio, not a constant difference. The logarithm is the tool that sees through the explosion and reveals the constant rate underneath. On a log scale, this curve is a straight line. The slope of that line is the growth rate. The logarithm does not hide the danger. It measures it precisely, while the linear scale is still showing you near zero. We have seen the same curve appear 3 times now. In the compounding limit, in the bacteria dish, and in the epidemic. Each time, the setting was different. But the mathematics was identical, something growing at a rate proportional to its own size. And each time, the natural logarithm was the inverse. Given where you are now, tell me how long you have been growing. E. coli, continuous growth rate 0.0347 per minute. An epidemic, growth rate 0.55 per day. Different units. Different biology. Same formula. The natural logarithm is not a human invention. It is what the mathematics of continuous proportional growth produces when you ask it a single question: how much time has passed? The bacteria or virus did not choose it. The universe simply has no other answer.